Connie Crete, a brilliant young engineer, stared at the cracked concrete cylinder on her lab bench. It was supposed to be strong, a testament to her skills. Instead, it looked like a sad, gray biscuit. "It's just not working," she sighed. From across the lab, the wise Professor Ashworth smiled gently. "Perhaps you are missing the secret ingredient," he said, his eyes twinkling. "The secret," Professor Ashworth began, holding up a small jar of fine gray powder, "is flyash." Connie frowned. "Ash? Like from a fireplace?" The professor chuckled. "Not quite. This is a high-tech powder, born from the fiery heart of a power plant, and its family tree is surprising. According to the technical standards, its journey can begin not just with coal, but sometimes with things you'd never expect, like petroleum coke or even municipal sludge." Connie's eyes widened in disbelief. "Sludge? You're telling me the key to stronger buildings might come from that?" Professor Ashworth nodded. "It shows that fly ash isn't just waste. It's an engineered product, precisely controlled no matter its unusual beginnings. It's all about transformation. But you must understand, not all fly ash is the same," the professor continued. "They have different personalities, or classes, as the ASTM-C 618 standard calls them. There's Class F, a clever chemical scavenger. When cement hydrates, it leaves behind a less useful byproduct. Class F reacts with that leftover material to create more of the strong, cement-like glue. It's a master of microscopic recycling." "Then you have its cousin, Class C," he added, drawing another diagram. "Class C is also a scavenger, but it has some cement-like properties of its own. It can harden and set all by itself when mixed with water. Choosing the right class is critical. It affects everything from setting time to the final strength of your concrete." "So it's not just a cheap filler to save money on cement?" Connie asked. "A common misconception," boomed the professor. "The standards insist that fly ash be an active contributor. We test this with the Strength Activity Index. A mortar with fly ash must achieve at least 75% of the strength of a pure cement mortar. It's not a freeloader, it's a powerful teammate." "But here is a paradox of our profession," Professor Ashworth said, leaning in. "The standards themselves, like ASTM-C 311, openly admit a fascinating truth. Our perfect laboratory tests are not intended to simulate job conditions. The chemical limits we set don't perfectly predict how the fly ash will perform in the real, messy world of a construction site." Connie was stunned. "So all these precise tests, they don't guarantee success?" "They are our best guide," the professor replied, "but they remind us that engineering is both a science and an art. The lab gives us the rules, but the real world provides the exceptions. It highlights the complexity of material science in practice." "To truly appreciate the precision, consider this," the professor said with a final twinkle in his eye. "The standards are so detailed, they even warn us how to pour the sand for our test mortar. You must be careful not to create little mounds or craters, because the coarser particles might roll down the slopes and segregate. The integrity of the test depends on it." Connie looked back at her broken cylinder, but now she saw it differently. It wasn't just a failure, it was a puzzle. She understood that the gray powder in the jar wasn't just ash, it was a microscopic marvel. The concrete all around her wasn't just stone, it was a testament to a hidden science, where even the way you pour sand could be the foundation of a skyscraper. She couldn't wait to mix her next batch,